Hello YouTubers, in this video I want to show what does it mean to say rocket science, and the second part of this video is about Laval nozzle cross-section area calculation. The rocket combustion chamber is made up of two parts: the combustion chamber where a controlled explosion of fuel and oxidizer occurs. An extra device is a Laval nozzle, or a diffuser. Is just the fancy name of pipe diameter increased along its total length. It's just truncated conical shaped device. We need to use air quotes on word device because device is something complicated. Card, smartphone, computer, rocket module, rocket engine, even pump or turbine are devices. The truncated cone is one of the basic primordial geometrical shapes. Over time, truncated cone device became a staple and even as a symbol of rocketry. This basic primordial shape is the most important device in all rocket equipment. This device describes how efficient a rocket is. Being a very simplistic device, mathematics and physics behind this basic shape are very sophisticated and complex. When people say hard or easy, they project subjective opinion, but behind this device is a really complex mathematics. Starting point of derivation starts from uniform flow rule for different diameter pipes. Here M1 and accordingly M2 is mass flow rate in the combustion chamber, and is the same flow rate in Laval nozzle too. Rho critical density of expanded gases in the thermodynamical process of adiabatic expansion of fuel and oxidizer mixture. Capital letter A critical cross-section area in the narrowest part where gases entering the Laval nozzle. W critical velocity in the narrowest cross-section area part. Rho gases density value in the exit from Laval nozzle. W velocity value from the exit of Laval nozzle. Capital letter A cross-section area from the exit of Laval nozzle. Our goal is to calculate the area of a Laval nozzle in such way that rocket energy velocity must be at the maximum value. The essence of Laval nozzle is that in uniform flow thermodynamical parameters of density and velocity in the entrance to nozzle and exit are different. Our goal is to increase velocity of gases from the exit of nozzle. W. A high velocity of expanding gases is directly related to the high velocity of a rocket. Please to see my first part video titled Rocket Science. High velocity means high efficiency of burning fuel and oxidizer mixture. In the process of adiabatic air braking or stopping, air molecules heat up. We know that gases enthalpy can be expressed in such way. Here, C with index P is specific heat of gases in an isobaric thermodynamic process. Inserting newly derived enthalpy expression into the equation above, and we get such temperature expression. This equation explains that in the entrance to the Laval nozzle and exit temperature must be smaller, and adiabatic processes are the same except breaking of gases increases gases temperature, whereas in the process of acceleration temperature decreases. Example, stopping of the gases from initial temperature 20 degrees Celsius with initial velocity 100 meters per second to complete stop, gas's temperature will increase by 5 degrees Celsius. The opposite is the true about if we have gases in the stagnant velocity state, 0 meters per second, and we accelerate them to velocity 100 meters per second, temperature will drop by same 5 degrees Celsius. That is our goal, to accelerate burning fuel gases in the Laval nozzle from critical velocity to W as fast as possible, but not changing fuel consumption rate of a rocket engine. To go further, we need two very useful equations used in ideal gas thermodynamics. That is Mayer equation, where C index V is specific heat constant in the isobaric thermodynamics process, and capital R is universal gas constant. And another important constant is K, the adiabatic process exponential. For example, for air, in our case, for hydrogen and oxidizer oxygen exhaust gases made entirely from 3 atomic gases water vapor, and the adiabatic exponent is equal to. From universal gas constant R, we express isobaric specific heat constant C index P, and from the adiabatic exponent we express isochoric specific constant C index V. Inserting C index V expression into C index P equation, and after terms rearrangement, C index P is equal to such expression. Insert this equation into the acceleration and breaking temperature equation, and we will get such expression of gas's acceleration or breaking temperature value. Divide last equation by temperature T and we get such expression. Here A is speed of sound constant and capital letter M Mach number criteria. We can avoid Mach number without any problems, but equation with such simplification of velocity divided by speed of sound constant looks neater expression, and one thing have in common mathematician majors and physics majors are neatness for math expressions. Mach number criteria gives opportunity to compare a gas flow to the speed of sound constant. Speed of sound constant in various temperature environments are equal to. Later we insert the speed of sound ratio constant into a temperature ratio equation, and we get a speed of sound constant expressed through Mach and adiabatic exponent constants. We take such adiabatic process equation from physics textbooks or Wikipedia source. Express pressure ratio through temperature equation and we get such expression. Insert newly derived pressure into density equation, and after some mathematics manipulation we get such density ratio equation. Before starting to find the area of a Laval nozzle in the exit, we need to find critical values of density and speed. So we write all needed thermodynamics equation in one equation system. This equation will be necessary later. The critical velocity and critical density are when burning fuel gases velocity in the entrance to Laval nozzle is equal to the speed of sound. It also means Mach number equals to 1. And we get a new equation system in terms of critical values. From the uniform flow equation, we express areas ratio equation. To solve the exit area of Laval nozzle, first we express a ratio of densities. We will use a mathematics technique called multiplying by 1. We multiply by densities ratio and get such expression. Rearrange terms accordingly in such manner. A ratio of critical density and index zero density we express from equation system of critical values. And density ratio of density index zero divided by density is equal to the product of two density ratios in the end is equal to such equation. The same technique will be applied to the velocity ratios only with one additional step. Critical velocity ratio we multiply by two different types of speed of sound constant ratio. Rearrange terms in such manner. The critical velocity ratio we found from the critical values equation system. This velocities ratio we get from this equation system. And velocity W and speed of sound A ratio gives inverse Mach number value. In the end, the ratio of critical velocity by velocity W gives such equation. All needed values is derived. So finally we can solve cross-section area ratio between the entrance to the Laval nozzle and exit from it. To get a cross-section area, we need to multiply previously derived ratios of velocity and with densities ratios. And our final equation is equal to. We need to be honest, that is a lot of mathematics manipulation. We can say that is hard as rocket science. Every step we need to keep track of every mathematics operation. The result is very rewarding, just by fact that no calculus or higher mathematics involved. The hardest thing is exponential operations. If we go to history books, Swedish engineer Laval, who first used this phenomenon for practical purposes on turbines, so it is called a Laval nozzle. But calculus methods-based equations have been derived by French engineer Huguenot and Scottish engineer and physicist Rankine way before cars and internal combustion engines and way before rocketry started. Sometimes it is called Rankine-Huguenot conditions. We investigate adiabatic shock thermodynamics phenomena, explosion of fuel and oxidizer mixture, with a calculus approach. We will use visual method by plotting graph. This method is better and much intuitive to explain why the Laval nozzle is wide in the end and narrow in the entrance. That is just direct violation of Bernoulli principle of aerodynamics. If we want to increase velocity for liquids and gas, we must narrow down the cross-section area of a flow. So next step is an investigation of a graph of a newly derived cross-section area ratio equation. First, this plot is for water vapor gases, hydrogen and oxygen, or hydrogen peroxide as rocket propellant. The graph is divided into two parts: subsonic gas flow, this region here, and critical velocity region. It means that gases velocity in the entrance or choke point technical term in Laval nozzle enters with subsonic velocity. and velocity in a wider region of Laval cross-section behave close to Bernoulli law of aerodynamics. It means velocity slows down in wider diameter section, and exit from Laval nozzle speed is smaller than entrance into a curve, and curve will follow this curve tendency. If an entrance velocity is exactly critical and equal to the speed of sound, the velocity from Laval will follow the right side of the curve branch. Let's say our goal is to increase velocity 3 times from critical velocity. We need 4.8 times bigger area nozzle than critical entrance area. Energy conservation comes from fact that gases enter to critical cross-section area with a higher temperature and exit a nozzle with a lower temperature. The reduced gases temperature being transferred into higher velocity kinetic of gases, which propels rocket with higher velocity and higher efficiency. I promise to calculate the velocity of exhaust gases in the first part of rocket science video. 2000 meters per second is plausible, or maybe it is very small value. Initial hydrogen and oxygen mixture flame temperature according to the manual is 2660 degrees Celsius. From this maximum temperature in the combustion chamber very fast adiabatically expand gases, and in the entrance to Laval nozzle we assume that temperature will be about 2100 Celsius degree. Okay, we are entering the guessing game, but this partially true. First, combustion chamber must have enough volume to allow controllable explosion and expanding gases to decrease in temperature, but also not allow decrease enough temperature. According to the speed of sound formula, higher temperature gives a higher speed of sound, which is the same as critical speed value magnitude. Mach number in exit from Laval nozzle of such is equal to such value. The area from an exit from the Laval nozzle compared to the entrance area value is equal to exhaust velocity 2000 meters per second is not big value according to our calculation. Only we need to introduce a factor who not allows increase area indefinitely. Adiabatic gases expansion has an alternative name as an isentropic process. It means no heat losses with surroundings. A very big area of Laval nozzle in the exit is extra mass and high energy loss through walls of Laval nozzle. And final calculation is acceleration temperature in the adiabatic thermodynamics process. From 2100 degrees Celsius in the entrance to Laval nozzle to 753 Celsius degree. Still, exhaustion gas is very hot. It means a lot of burning fuel potential energy been wasted. On other hand, velocity increased more than 2 times. It means gases transfer heat into the useful kinetic energy of rocket as velocity. That is all, folks. Thanks for watching. Please subscribe.